Good morning, Year 12. So, today we're basically going to be doing some simple biological maths. And it's no one's favourite subject, but it is essential if you're going to do any future research that you understand some basic ideas on how to do some statistical tests to check whether an experiment is valid or not. I'm going to go into that in more detail in a second, but for now we're just going to start off by talking about two things, one of which you've definitely done before and I'm going to spend about 30 seconds on, and one of which you probably haven't unless you're doing maths, so we're going to spend a bit more time on, which is standard deviation. Start with mean. In order to kind of give you that idea, we're going to go back to our normal curve. Now the normal curve looks like that, and we talked about the normal curve when we were talking about biological distributions of variation. So when we're talking about variation, it tends to be that if it's a quantitative variable, something like height, weight, foot length, anything you like, that it will follow a normal curve. And that means that the mean is also the median, i.e. the value that is in the middle is also the value you get if you add them all together and divide by the number. And that's also the mode, so that value is also the most common value. But very broadly, you just need to know that it means that most people are dead average in the middle. Now, that means that 50% of values can be less than the mean and 50% are greater than the mean. And if we don't know mean, median, and mode, you are expected to for A-level biology. I'm not going to spend long on this. 30 seconds. Mean is what you traditionally call an average of your values. If you get all of your values together and divide by however many values you have, you'll have a mean. You're going to have to do some of those later on, so we're going to have a go at those for what it's worth. Median is the middle value. Now, that's quite useful if you have strange outliers, but tends to be we don't talk about it very much. And the mode is the most frequent value. Pretty much the only time we care about the mode is if it's a qualitative data, i.e. if it's something like eye colour, brown, blue, green, red, etc. You can't say what the mean is, you can't have a mean of brown and a half. There can't really be a middle value, but you can definitely tell me which one is the most common, and that's when that's useful. It's never useful for quantitative data. When you're calculating an average, pretty much 95% of the time it's going to be the median, the rest is going to be 95% is going to be the mean, the rest is going to be the median, and you're almost never going to be asked about the mode. Fine. The mean gives us an average value, and that's useful, but it doesn't tell you anything about the range of values within the sample. Clearly, there is a difference, if we look at that graph, between the red curve and the blue curve. If I said to you that the average height of a mole is 6 centimetres, you might go away thinking, well, all moles are about 6 centimetres, that's fine. But if it's the blue curve, then it's just that more than any other are 6 centimetres, but you can have 1 centimetre mole and 10 centimetre mole. If it's the red curve, then it really is that pretty much every mole is between 5 and 7 centimetres. So it matters how spread the data is. The mean number of eyes in humans is 2. If I drew that curve, it would be quite thin. Some people have 1, some people have none, some people probably have 3, but the vast majority of people have 2. We have a very thin little curve with a tiny bit of stretch. The average height of a man is just under 6 foot, under 1.8 meters. But that will have a lot more spread. Now, standard deviation enables us to tell how much spread there is. So a standard deviation is a measure of how spread out the data is around the mean. And broadly, the bigger the standard deviation, the more spread the data is. So there's a big standard deviation on that blue curve, and there ain't much standard deviation on that red curve. You have to know that, so please pause me and write that down. That's what that standard deviation is. Now broadly, if you have your mean, and you have a standard deviation, The mean plus or minus 1 standard deviation is about 68% of your sample. So if I add 1 standard deviation on each side, then I'll have 68% of the sample. So let's say the average height of men is 1.8 meters. It's not quite true, but let's say it was. Average height is 1.8 meters. And let's say the standard deviation is 0.1 meters. That's definitely not true, but let's say it was. 1.8 meters, 0.1 meters. That means 68% of men will be between 1.7 meters and 1.9 meters. 2 standard deviations is 95% of the data sample. So I could say that 95% of men are between 1.6 and 2 meters. And so that enables me to very, very easily work out what my maximum range is realistically going to be. So I can say the vast majority of people aren't going to be above 2 meters. But if the standard deviation was a meter, then I could say the vast majority of people aren't over 2.8 meters or under 0.8 meters. And that doesn't tell me much at all. So the smaller the standard deviation, the more kind of cropped your size is. Fine. Incidentally, you're not expected to know 68 and 95%. You just need to know the more standard deviation, the more spread your data is. Just so you can get an idea of the maths there. Unless you do maths, in which case you probably do need to know that. So you have to be able to calculate a standard deviation. And it ain't much fun, but here is your sum. It looks very complicated. Actually, if you break it down into pieces, it isn't that complicated. So, before you can calculate your standard deviation, you have to know your mean. So what you do is you get each value. So let's say I took the height of 30 men. I get each value, so the first one might be 1.8 meters. I subtract that from the mean, which is 1.8 meters. And I get 0. I square that, I get 0. I do that for every man in my sample. So for every man, I take their height, I take away the mean height, I square that, and then I add all of those together. This might become clearer when we do one. But this little symbol here, it's a Greek letter, I'm going to say epsilon, I might be wrong, I never really cared, means sum of. It means add them all together. Then you divide that by the number of people in the sample, 30, minus 1, 29. And then you square root the whole thing. So if you look at it like a whole sum, it's quite complicated, but if you take each little bit, it's not that hard at all. Let's do a couple. You are expected to know how to do this. It's extraordinarily rare that they would ask you to do an exam because it takes too long. They would have to give you lots and lots and lots of marks, and they'd have to give you this formula, so it's quite simple as well. So they never do that. But you do technically need to know how to do it, and if you want to do any science or maths later on, you absolutely will need to know how to do a standard deviation, or any research of any kind, medical research, psychological research. Fine, let's do one. So, follow the steps then. So, first we have to calculate our mean. So calculate this mean. Please pause me. Probably the best way to do this, draw out the whole table, and then can you calculate the mean of these, please? Thank you. Just pause me and have a go. So hopefully you calculated that the mean was 15 divided by 6, or 2.5. So, the first thing you then need to do is you need to fill in this column with your x minus x bars for each sample. So, I'll give you the first one. The x here is 4. It's just the it doesn't tell you what it is, but the height of the man, whatever it might be. 4 minus x bar is the mean, remember. So 4 minus 2.5 makes 1.5. So this here should say 1.5 because you've done 4 minus the mean. You then square that. 1.5 squared is 2.25. So this should say 2.25. I'm hoping I've done my mental maths correctly there. So that should say 2.25. You can do this for every set of data, please. So do the value minus the mean and then square it. Fill in this table, please. And pause me again to do that. Fine. So what we should have then is these numbers. Now, there's your numbers. What we then do is we do the sum of the x minus x bar squareds. So we just add all these together. And you can immediately do that now. There's no difficulty there. Just add these numbers together and you should have, I'll pause me and I'll tell you. You should have, apparently I won't tell you. But you should have 17.5. Let me make that work. Okay, the magic of video editing, 17.5. Fine. So that is the sum of x minus x bar squared. You then divide that by n minus 1. Now remember, n is the number of samples. How many samples were there? Well, there were 6. n minus 1 therefore is 5. We do 17.5 divided by 5. And then we square root that, which you'll need a calculator for, I should imagine. No, I can't do it off the top of my head. So we should have, is it 3.5? Root 3.5? Yeah, 1.87 is the answer. Now, that's standard deviation. Standard deviation is 1.87, and that's as simple as it is. It's not simple, is it? But it's not as complicated as this sum makes it look. We're going to do one more, and then we're going to do quite a lot, unfortunately, over the course of the next few lessons because they are really essential. But before we do the one more, okay, so that's just applying the data you got. So 68% of the values will fall in the range of the mean 0.63 to 4.37, and 95% of the values will be between minus 1.2 and 6.24. Fine. Right, here's the key point. We draw on graphs error bars. And you would have seen these, even if you haven't understood what they mean. Error bars just show either one standard deviation or occasionally one standard error, and we'll come to that next lesson, on each side. So you can see on 4 of these bars, the standard deviations are quite small. And they should stretch up and down, but they've put little faces on there to make it funny, if we think that's funny. But the key point is, the bigger the standard deviation, the less likely it is that the mean recording you have is accurate. For C here, the mean is 50, but the standard deviation is so high that actually, really, the actual value, if I record everybody in the world, might be anything up to 100 or down to 0. The error bars tell you where the true mean is likely to arise if you are collecting a sample. So the bigger the sample size, the smaller your standard deviation will be. And you can see that in the sum. You can see here, n minus 1 is on the bottom there. So the bigger n is, the smaller your standard deviation is. This is why we need large sample sizes in experiments, because the more samples you do, the smaller your standard deviation, the more likely it is your data is accurate. Unless you are counting everybody in the world, or everything in the world, there is always some uncertainty. Maybe you've accidentally counted all the short people and none of the tall people. Maybe your mean is actually slightly higher. And basically, your mean is likely to fall within this error bar. So looking at this without error bars, you would think, right, okay, whatever I'm measuring, B is the smallest, followed by C, followed by D, followed by A, followed by E. But because the error bars are so massive on C, C could actually, if I measured it properly, be up to 100. And so realistically, C could be the biggest, not the second smallest. And if the error bars overlap, that indicates that the samples may not be significantly different. So let's say I'm doing, let's take height again, it's a nice easy example. Let's say I'm doing the height of various ape species, and I take 10 of each of the ape species, and this is the data I got. I can confidently say that E, whatever E is, orangutans, are taller than D, because these error bars do not overlap. So even if E was at its very lowest, around 78, 79, and D was at its very highest, around 55, 56, D is still going to be significantly smaller. With C, though, those error bars are so large that I can't say with any confidence that E is actually taller than C, because C could really be up to 100. If I've got two random apes, one from E, one from C, these error bars suggest that there's no certainty that C will be smaller than E. But there's a great deal of certainty that, for instance, B would be smaller than A. If the error bars overlap, then it's probable they're not significantly different. Okay, we will come back to that in a lot of detail next lesson when we talk about a statistical test called the student t-test. So please don't worry if you didn't get that necessarily immediately. Some people will have found it very easy, some people will have found it more difficult to understand, depends on their brain. But let's do one more, as I said we would, and then we'll be done with this and we will have the rest of the lesson to do whatever you need to do. So, I say four more, unfortunately. I'd like you to, for each one, calculate the mean, the standard deviation, and the mean plus or minus one standard deviation. So basically you'll have two values, 1 plus 1 standard deviation and 1 minus. If you don't follow that, just leave the third column for now and do these two, they're the hard ones. So I will give you, I reckon it would take you a good 5 or 6 minutes this. Once you've done all four, hopefully it'll be quite straightforward. If you'd like to though, if you're not feeling confident, you can pause me now and have a go at the dandelions. I will go through the dandelions, well, about 5 seconds for me, but after you finish pausing, and then I'll let you do the other three. So, the mean is 2 add 1 add 3 add 2 add 1 divided by 5, which is 1.8. I'm confidently told. If the maths on any of this is wrong, I apologise. I did do this a long time ago. I think it might actually have been Miss Hussey. So, if it's wrong, tell me. The standard deviation, right? We take each of these, we subtract the mean. So we do 2 minus 1.8 squared. We do that for each one. We add it all together. So we have 2 minus 1.8 squared, add 1 minus 1.8 squared, add 3 minus 1.8 squared, add 2 minus 1.8 squared, add 1 minus 1.8 squared. Now if you're going to be in a hurry and you're going to do each of that as one sum on your calculator, make sure you've got your brackets in the right place. You don't want to square it each time, you'll get an enormously high value. Put your brackets. Fine, and then you divide that by n minus 1, which would be 4, because 5 minus 1 is 4, and then you square root it, which gives you a number of 0.84. If you don't follow any of that, rewind the video to when I went through the equation. Or if you'd like to type in how to do a standard deviation online, perhaps you could find a written example of that to make it easier for you. Mean plus 1 minus 1 standard deviation, I mean that the range is likely to be between 0.96 and 2.64 for the actual mean of dandelion frequencies. Right, now pause me again and have a go at the other three, unless you already did them, in which case just keep playing video. So, what you should have got is that, and that. So, I don't know, there's not a huge amount to say about that, is there? If you got them right, congratulations, well done. If you got them wrong, then you need to go back and check your sums again. Usually it's that you haven't put brackets in the right place, you've squared something after dividing it or something funny like that. Or sometimes people forget to square it after sum of x minus x bar. Sometimes people forget to square root it at the end. So, difficult to say what you would have done wrong. Go and check your sums again. And again, if you got it completely wrong, go back, rewatch that bit of the video, that 5 minutes, about 10 minutes ago, and make sure you can do one of these by the end. There's the means as plus or minus 1 standard deviations as well. What does it mean? Well, it means that Definitely, daisies are the most frequent, because even with the maximum range here, they're still dramatically higher than the others. What it means for the others, even though the means made it look like it was buttercup, then plantain, then dandelion, these ranges all overlap. So plantains is somewhere between 0.2 and 2.2 per unit size. Buttercups are between 0 and 2, and dandelion is between 0.96 and 2.64. So that could mean that they were all exactly 2, and they'd all be the same. Or it could mean that actually there's only 0.2 plantains, but there's 2 of each of the others. Because until I've literally counted every single plantain, dandelion, daisy, and buttercup, there is always uncertainty, and the standard deviation indicates how much uncertainty. It indicates the rough value of the range. And if I drew this as a graph, I would have the bars as the means. I'd have 1, then 1.2, then 1.8, and then 5.4. But I'd have the error bars showing between 0.96 and 2.64. I'd have a big error bar there. Between 0 and 2, a big error bar there. And 0.2 and 2.2, a big error bar there. Right. That's all I'm going to do on this for today. We are going to do another one of these next time on the student's t-test. If you got them all wrong, and you're not sure where you went wrong, you can feel free to contact me, or you can go online and get yourself some questions on these. There will be literally hundreds and hundreds of questions on this. If you type standard deviation questions online, because the maths GCSE does it, the biology GCSE does it, even the psychology GCSE has to do it. So you'll be able to, A-level for each of those. So you will be able to find some questions. Don't worry about that. And have a go at them. Check your exam mark schemes. But otherwise, as I say, contact me, and I will see if I can help you. Hopefully that's been straightforward. Looking forward to seeing you all at some point in the near future.